Thanks, Timo. So today we'll talk about the dynamic compass code. So when I say compass code, it means that it's a construction framework based on two-body Pauli generators acting on neighboring qubits with orientation. So here in this specific example, we use horizontal for XX and vertical for ZZ. And these generators are interpreted as gauge operators. So you can get your stabilizers by grouping the gauge operators that you want. So a particularly simple example of the compass code is Bacon-Shaw code. So Bacon-Shaw code arrange qubits on the grid and perform parity measurements on the adjacent qubits. So here, it performs the XX parity measurements on the horizontally adjacent qubit and ZZ parity measurements on the vertically adjacent qubit. And these measurements form the gauge group of the code. So here I use the instantaneous stabilizer groups to mean the Pauli operators that commute with all the measurements up to the current time step, and any operators that anti-commute with the newly applied measurements are removed from the stabilizer group. So here, in this 2x2 Bacon-Shaw code case, we firstly perform the XX pair measurements on the horizontally adjacent qubit. So these enter the stabilizer group. And then in the next time step, we perform ZZ parity checks on the vertically adjacent qubit. And these, since obviously the measurement we performed before is anti-commute with the newly applied measurements, therefore the XX pair measurements are removed from the stabilizer group, and the product of them remains in the group because they commute with the newly applied measurements. So here at the next time step, we again perform the XX pair measurements, and these XX pair measurements enter the stabilizer group, and the ZZ pair measurements are removed, and the product of the ZZ pair measurements remains in the group, stabilizer group. So this repeat periodically. So in the instantaneous stabilizer group, at any time step, it will only contains the measurements you performed and the stabilizer that commutes with the measurements you performed. So this is the logic operator of Bacon-Shaw code. So ZZ horizontally for the logic Z and XX vertically for the logic X. So let's see a larger example, which is not much larger than the 2x2 case. So this is the 3x3 case. So here we use the same measurement pattern as the 2x2 case. So we perform the horizontal XX pair measurements. So we perform the XX pair measurements on the horizontally adjacent qubits and ZZ pair measurements on the vertically adjacent qubit. So the only difference between the 2x2 and 3x3 case is the size of the surviving stabilizers. So in the 2x2 case, the size of the surviving stabilizer acts on 4 qubits, and in the 3x3 case, we have the size of the surviving stabilizer that acts on 6 qubits. So in generally say, the size of the surviving stabilizers grows linearly with the code of the size of the code. So this actually becomes a problem when the grid size goes upon to some points. So this is the logic error rate plot for the normal Bacon-Shaw code. As you can see here, to some point it starts to curve up, and this is because of the when the stabilizer gets larger, the noise of the measurement noise start to accumulate in the stabilizer, ended up to some point that the stabilizer is unreliable anymore. So in order to solve this problem, less Baker-Morse threshold, this paper, less Baker-Morse threshold, try to concatenate small Bacon shortcode into large Bacon shortcode. So by this way, so here, as you can see, this is the pattern of pair measurements over time. And here the axis shows you the time that when you perform the measurements on the column or the rows. So here, obviously, as you can see here, they measure the gap of the two small Bacon shortcode much less than when they measure the small Bacon shortcode itself, and they measure the large gaps much less frequently than they measure the small gaps as well. So this is the numeric result of the construction in less Baker-Morse threshold. So here, this is a plot that plot the logic error rate for different code sizes. And the fractal pitch means the size of the small Bacon shortcode they concatenate. And the third rate hold factor means the rounds that they measure the little gaps. So here, when the third rate hold factor equals to 1, means at this time step, they measure the whole column once. And here, when the third rate hold factor equals to 5, means they measure the whole gap 5 times so 5 rounds at this time step. So in the paper, they expected to see that when you have larger third rate hold factors, you can have better performance, as here. But however, in the numeric simulation results, when you have less third rate hold factors, you can have better performance. So this is the instantaneous stabilizer group of the less Baker-Morse threshold construction in different time steps. As you can see here, the right highlighted area are the X stabilizers which goes vertically, and the blue highlighted area are the Z stabilizers goes horizontally. So when you have larger third rate hold factors, means you give more chances. You will increase, actually, when you measure the whole things more times, and then it gives you your code more large stabilizers. So that's why we think it's the reason why the third rate hold factor, when the third rate hold factor became larger, the code performance became worse. So here, also, like as you can see here, they still have the large stabilizers exist in this construction. So we start to ask us a question. So is there a new measurement schedule that's possible? Can we avoid to have the whole column or the whole row stabilizers? And can we achieve the constant size detectors? So this is the problem we solve in Bacon short board games. So these are the two cool people that works in the project. So in this project, we give the Bacon shortcode a new measurement schedule. So here, as you can see here, the data qubits are on the vertices, and the red segments represent the XX pair measurements, and the blue segments represent the ZZ pair measurements. So here, instead of measuring all the neighboring qubits, we only measure the selective subset of the pairs. So for this reason, we need 4 time steps to finish a full complete measurement rather than the 2 time step that in the original Bacon shortcode. So this is how the instantaneous stabilizer groups evolves with time. Maybe it's not that clear, but yeah. Okay, so here, the red dashed line represent the measurements we performed from the last time step. And this red dashed line is used as a reference. And the same for the blue dashed line. These represent the ZZ pair measurements we performed from last time. So it's also for reference. And here, the color is not that obvious. So the red highlighted, okay, this is red. So the red highlighted area represent the X stabilizers, which goes vertically, and this is blue color. So the blue highlighted area represent the Z stabilizer, which goes which goes horizontally. So X goes vertically, Z goes to horizontal, goes in the horizontal direction. So here, as we can see, we do not have any stabilizer go across the whole column or the whole rows. So by this way, we achieved constant size stabilizers. So this is how we form the detector inside of the code. Here, we only consider the measurement we've done in the first column, and we only care about the X stabilizers. So here, in the first time step, we perform the X pair measurements in the first column. So we will have the single XX pair measurements in our stabilizer group in the step 1. And in the next time step, we perform the corresponding ZZ pair measurements. And these ZZ pair measurements group the top 3 XX pair measurements together. And this groups the bottom 2 together. So as you can see here, you can see here, these are grouped together by the product dot. And in this time step 3, we again perform the XX pair measurements, but this time we only perform it on the qubit 16 and 17. So these measurements deconstructed the previous stabilizers into 2 stabilizers. Here is again X21, X22 from the first time step, and X16, X17 was the newly measured X pair measurements. So in the first time step, we again measure the ZZ pair measurements, and this time the ZZ pair measurements group the newly measured X16, X17 into the 6 qubit X stabilizers. So, and this stabilizer can be reconstructed by the measurements made in step 5, and therefore it became a detector. So this is a worksheet showed the evolution of the instantaneous stabilizer group in the space-time. So here it's the same as the previous example. We care about the X stabilizers in the first column. So here, first time step, we made the X pair measurements. So here we have the red segments represent the X pair measurements in the first time step. And next time step, we perform the corresponding ZZ pair measurements, and these ZZ pair measurements group the X pair measurements in the first time step. So the shaded area X shows how the instantaneous stabilizer group transform over time. So again, in the third time step, we measure the X16, X17 here. And the next time step, we perform the ZZ pair measurements, which group the X16, X17 into the 6 qubit X stabilizers. And this stabilizer can be reconstructed by the measurements in the fifth time step. Therefore, this closed cell became the detector. So this is the same plot, but for the detector at the bottom of the first column. So let's see a real larger example. So here is a modified baking shortcode with the grid size 10 by 10. So here, as you can see here, we do not have any stabilizers that go across the whole column or the whole rows, even in a large grid. So our stabilizers stay in constant size and do not increase with the size of the code. So, and this is the boxed area has the same instantaneous stabilizer pattern as in the 5 by 5 case, and the stabilizer does not go beyond of the box. So actually the detector stay locally as the 5 by 5 case and do not increase with the growth of the size. So this is the noise model we use for our simulation. We just simply use the uniform noise model, which in the noise, for the noise channel, we have the same noise probabilities for all the noise channels, and we replace the ideal gates by the noisy gates. So here is the result of a numeric simulation. Here, this plot shows the logical error rate for different grid size, and the blue curve is the simulation result we got for our Baking shell code, modified Baking shell code. As you can see here, it clearly shows exponential suppression of the logical error rate with the increase of the grid size. And this is the result from the construction from the less Bacon-Moss threshold, which also shows improved compared to the original Baking shell code. The performance was affected by the large stabilizers in the code. So this is our plot that shows the logical error rate is a function of physical error rate. We observe a clear cross point at the physical error rate of around 0.3%, which is the threshold that we observed. So this is the conclusion for this project. So we introduce a period 4 measurement schedule that enables us to get the constant weight detectors. Also, we achieved the threshold, which is around 0.3%, under uniform circuit level noise. So similarly, for the heavy hex code, they actually have similar problem as the Baking shell code, where the use of large stabilizer increased the impact of the measurement noise and reduced the code performance. So here is a heavy hex lattice. Here, the big black circle represent the data qubits. The small black circle represent the ancillars, and the white the white square represent the X ancillars. So the measurement of the heavy hex code are represented by the highlighted area, which is not that clear here, but yeah, okay. So the blue highlighted area indicate the ZZ pair measurements, and the red highlighted area represent the 4-qubit X measurements in the heavy hex code. So this is an example of the example circuit for the 4-qubit X stabilizers. So in order to measure the X stabilizers, we need to initialize the X ancillars into the plus basis. And by a sequence of CNOT gates, the X operator propagates to the Z ancillars and finally onto the data qubits. So you can measure the ancillar out to get the measurements of the stabilizer. And this is the, wait, where's my mouse? Okay. And this is the example circuit for the ZZ measurements. So we initialize the Z ancillars into 0 basis, and the Z propagated by the CNOT gates onto the data, and we measure the Z ancillar out. So there's also flag qubits exist inside of this circuit. So if an error occurs on the Z ancillars, this arrow can be propagated onto multiple data qubits. And this actually can reduce the effective code distance. However, by measure out the flag information, we actually can prevent this reduction in the code distance by using the information we got from the flag measurements. So this is the ISG evolution over time on one row. So here, we measure the 4-qubit X stabilizer first. Wait. And then we measure the ZZ pairs here, which is not obvious, but yeah, there's a blue highlighted area here. Shows that we measure the ZZ pairs. And because of the ZZ pairs, because the X stabilizers are anti-commute with the ZZ pairs, so we remove them from the stabilizer group, but the product stays. And then we again measure the 4-qubit X stabilizers. So in this case, the ZZ pairs are anti-commute with the X stabilizers. Therefore, the ZZ pairs are removed, and only the product of the ZZ pairs remains in the stabilizer group. So actually, the original heavy hex lattice is kind of visually complex. So we simplify it to the simple lattice. So here, as you can see, the red area represents the 4-qubit X stabilizers, X measurements, and the blue segments represent the ZZ pair measurements. And the data qubits are on the vertices of the lattice. So here shows the ISG behavior over time for the entire heavy hex code. So the first row we shows the measurements of the heavy hex in each time step, and the second row we shows the stabilizers for the heavy hex corresponding to each time step. So first time step we have the X stabilizer measured, and then we measure the 4-qubit X stabilizers, and then this goes to the stabilizer group, and then we measure the X ZZ pairs, and these ZZ pairs group the whole row of X stabilizers together. And then we again measure the 4-qubit X stabilizers, and these X stabilizers anti-commute. So the ZZ pairs group together. So this area actually a blue color that shows the 4-qubit Z stabilizers. And then again we measure the ZZ pairs. So this repeat periodically inside of the code. So this is the numeric results based on the original heavy hex code. So here, this shows the logical rate in X spaces. In X spaces means that the stabilizers are in X spaces. So here, as you can see from the stabilizers, so the X stabilizers actually has a Bacon-Shaw code behave. And the Z stabilizers actually behave like a surface code-like structure. So since the stabilizer in the X spaces behave like a Bacon-Shaw code, therefore we didn't observe a clear cross point here. Therefore it does not have a clear threshold here. And however, in the Z basis, which has the surface code-like behavior, and therefore they have a clear cross point here. So in order to solve the same problem as the Bacon-Shaw code, we start a new project called Dynamic Heavy Hex Code. So these projects are done by these super smart and brilliant people. So in this code, we use the same strategy as in the Bacon-Shaw board games. We only modified the schedule of the code without modifying the code layout. So here we keep the 4-qubit X measurements the same, unchanged, and then we perform the ZZ pair measurements on only the subset of pairs that we choose, and then we perform the X stabilizers again, and we perform the ZZ pairs in the second group. So for the same reason, we have 4 time steps compared to the original heavy hex code. So here is the instantaneous stabilizer group behavior over time. It's the same as before. The first row represents the measurement we've done, and the second row presents stabilizers. So here I use the round start from here I use the second round rather than the first round, because after the second round the stabilizer start to repeat periodically as in the second round. So here, as we can see, we perform the 4-qubit X measurements first. And now we perform the ZZ pairs. And the ZZ pairs will only group some subset of the X stabilizers together. And then also here, we only group the other subset of the X stabilizers together. So this is not, this this schedule is not unique. We also can use these schedules. So for this schedule, we also, as you can see here, we also do not observe any X stabilizers go across the whole rows. So actually, there is more choices for the choosing of schedules. The key point in designing the schedule is to decide which stabilizer. Actually, this is, as you can see here, it's not white, it's blue color. Well, blue. So the key thing is to decide which stabilizer you want to preserve from the last time step to the next time step. So here, in this example, the purple square are the stabilizers that we decide to preserve, the Z stabilizers that we decide to preserve. And in order to preserve these stabilizers, the main point is do not measure any ZZ pairs that might deconstruct your Z stabilizers. So in simple words, do not measure the pair measurements on the top or the bottom of the stabilizer that you want to preserve. So by this way, you can choose any stabilizer that you want to preserve and design the code based on your own needs. So we did evaluation based on 2 different schedules. This is the first one. So in this one, we choose half of the Z stabilizers that we can preserve. So this, as you can see here in the left panel, the red highlighted area represent the Z stabilizer that we want to preserve in the first group, and this is the rest of the Z stabilizer we preserve in the next group. So here, as we can see here, this is the numerical result based on this schedule. We have the plot that we plot the logical error rate as a function of the physical error rate. And as you can see here, in X spaces, we also observe a clear cross point. And this is actually at the cost that the performance reduction in the Z basis. So the cross point of the Z basis actually goes a little bit worse than before. And in order to compare with the previous example, we choose, now in this example, we choose only a quarter of the available Z stabilizers as the preserved stabilizers. And in these cases, we choose less preserved Z stabilizers, and the result is obvious. We can see that in X basis, we have a threshold lost. And in the Z basis, we actually have a performance increase. So there's an obvious trade-off between how many Z stabilizers you want to preserve and the performance in X basis and Z basis. So in this project, we use a modified measurement circuit designed by Robin compared with the original heavy hex implementations. So the choice is motivated by the constraint of the IBM quantum Marrakesh device, where the measurement operations have relatively long durations. So therefore, we use a compressed measurement mode circuit, which extracts the synchrone of the stabilizers at the same time. And by this, we can reduce the idle time and lower the corresponded idling noise. So here I showed how the X stabilizer was constructed in the circuit. So firstly, it goes the same. It goes on the Z ancillar qubits and then goes on the data qubits, and then we constructed the Z stabilizers. So as you can see here, the measurement at the same time refers only to the simultaneous readout of the measurement outcome. As shown in the circuit, we still prepare the X stabilizer first and then the stabilizers. Therefore, the measurement is not, so we only read out the syndrome at the same time. The measurement itself is actually not performed at the same time. So for this circuit, we do not really have a flat qubit because the error occurs on the Z ancillars does not really propagate onto onto multiple data qubits. So as you can see here, it will be canceled out by another CNOT gate here. So like this measurement extraction circuit does not intrinsically save from the arrows that propagate on the Z ancillars. So on the Marrakesh device, the reset is implemented as a conditional reset, which consists of a measurement followed by a classical conditional X gate. So this is the equation that you can calculate the reset noise. If you're interested, you can read the paper. So since on this device, the measurement time dominates the duration of the syndrome extraction rounds, we can actually remove the unnecessary measurements from the circuit in order to reduce the impact of measurement-induced idling noise. So this can be achieved by remove the resets in the circuit. So this new circuit can be supported by only modify the detectors. So in this case, you compare the detector to run in advance rather than the immediate previous run. So the reason is following. Where's my? Okay. So if we have an error occurs on the data qubit, this will flip the syndrome measurement. And without a reset, this will keep and again flipped by the same arrows propagated from the first round. And if we only compare the measurement results in between, it actually indicates you that there's new errors happen in round 2, but which is not true. But if we let the error propagate to the round 3, so the same error will flip the syndrome result again. So by comparing the round 1 and round 3, we actually can get the detector correctly identifies the original arrows we want. And so this is a noise model of the device. So here we did some simulations. So here we fixed the one qubit depolarized noise because it's the least significant noise among all the noise, and it's also affect the circuit the least. Therefore, we fix this, and we also, by fixing this set of 2 qubit depolarized noise and the measurement noise, we extracted the idling noise threshold. So every single circle on the plot represents one such simulation. And the shaded triangle represents the quadratic fit of the surface. So the region below the triangle shows the correctable region, that any noise ended up here this code can be the logic error rate can be suppressed by increase the code size, but above this region is uncorrectable region. So this is done with the reset. Okay, just make it animated to look fancier, but yeah. So this is the same simulation in the Z basis with the reset. So the summary of this project is that we modify the schedule for the heavy hex code and introduce a threshold against Z arrows without significantly compromising the performance against X arrows. And however, as we showed before, the the protection against the errors could be changed by removing the resets in the circuit. We haven't done this yet, so don't know how the performance would look like. And also we modified the schedules that can also be used to mitigate the effect of the defective or more noisy individual qubits in the device. Thanks for listening.
Thank you, June, for the talk. Are there any questions?
Thanks for a great talk. So I think on one slide for the heavy hex, you have like the logical X and the logical Z, and on one of them you said like it indicated there wasn't a threshold, and the other there was.
Yeah.
Too far back, but to see that, how does it indicate that? Sorry.
This one?
I think so.
Yeah, sorry, what is the question?
I think, did you say that one indicates that there is a threshold and one indicates there isn't?
Yeah.
How do you see that in the one?
So one does not really have a clear cross point. So it can actually cross in different places. And one has a very clear cross point.
Thanks for the nice talk. In the earlier project on the board games, and also this one,
Yeah.
in all of these like in the instantaneous stabilizer codes you get, they're not like obviously surface code, but are they equivalent to surface code?
Sorry, is it?
In both parts of the talk, like the first part and the second part, you get like you're doing some dynamical code, and you get some instantaneous codes, and you kind of show the stabilizers.
Yeah.
But they're not like obviously surface code. But are they equivalent to surface code?
No, actually, the first one is not equivalent to surface code, and the second one is showed. So here, only the stabilizer patterns and the Z basis shows the similar, patterns as the as the surface code, but this one doesn't really.
That's for the regular heavy hex code, right?
Yeah, this is from the regular heavy hex code.
Oh yeah, but I'm interested in your dynamical code that has low weight detectors.
Okay, so these are also not similar to. These are also it's also not equivalent to the surface code. So.
But is it equivalent to like a local unitary circuit or something like that?
Sorry, entire circuit.
Is it equivalent if you apply like a local unitary circuit? It seems like it encodes one qubit in a similar way to surface code.
Yes, we can talk about later. I didn't really understand the question, sorry.
So I have a conclusion on this, like the basic Bakery short code. The Bakery short code, the simple measurement circuits, they are just measuring the check operators, right? So why does long stabilizer weight in ISG matter?
You mean that we only measure the pairs, why the long stabilizer matters in the ISG? Is that your question?
What's the issue with large weight stabilizers if they're always measuring the check operator?
So when we measure the pairs, actually each measurement has some measurement noise. So when you multiply more of these pairs, you actually ended up with the accumulation of the noise. So to some point, it started to be not reliable anymore, the result of the stabilizer, yeah.
Maybe I can ask a question. So this is nice because you can like make a threshold. Have you thought about what it does to like the time-like distance?
You mean for the time access, what does it do? So you mean in the modified cases?
Yeah.
So actually, it will make the detector range longer for the both side.
Mm-hmm.
So yeah, so that's why the performance, as you can see here in the modified heavy hex code, the performance of the Z basis start to become worse because of once you extend it to longer in the timeline. So the detectors became long range. That's when the performance became worse.
Yeah, I think I thought what I was thinking about is like if you would do like a stability experiment, so one that like does not check for like X or Z logical flows, but for like time-like logical errors, like these things that are like relevant in like lattice surgery, for example. Like typically in like service codes or something, you would have to like repeat measurements like over D rounds. In this case, you still have to like over like 4D cycles, or do you even have to do like more? Do you know like how many rounds you have to repeat these measurements?
Well, I don't know how many rounds we need to repeat. I just use the 4D rounds as what they did in the last Baker-Morse threshold, and for all the codes afterwards, we just keep the same as what they did in the last Baker-Morse threshold.
I think it would depend on whether you're doing an XX or a ZZ. So you're always measuring your 4-body stabilizers,